Good afternoon, everyone. Welcome to the second talk for the Seismic Acquisition community. Hopefully, many talks will follow soon. This session will be recorded and made available on our EAGE community's YouTube channel. Please mute your microphones and switch off your camera to spare the bandwidth. Questions will be answered after the session. You can leave your question in the chat box on the right-hand side if you wish. Please let me introduce you to Luca de Vincenzi and Chris Walker and their co-presenters Nicolas, Tellier and Brice. Okay, Luca, you can start.
Okay, fine. Good afternoon, ladies and gentlemen. My name is Luca de Vincenzi. I work for the Geophysical Group based in Cairo. Today I have the honor to present the past marine sources to understand the present and future challenges in the offshore acquisition. Then, after a few words on the Sparker source, I will describe the conventional airgun and its improved versions. Finally, I will leave the stage to Dr. Walker, BTP Offshore, for modern vibrator and source methodologies. Dr. Timothy Brice, Shearwater Geo, and Dr. Nicolas Tellier, Sercel, will support us in this presentation. This picture gives you an idea about the differences of some past, present marine sources. Let's go through. Airgun ejects compressed air, unfortunately producing a bubble effect, which we discuss in details later on. Water gun is an inclusive source. Vapor shock uses steam, which creates forerun and main shock. Maxi pulse uses dynamite, aquapulse gas propane as energy, and flexi shock kinetic energy. This picture gives you an idea about the spectrum of the water gun is richer in high frequencies, more than 200 Hz, than are those of the air gun, but they also have less energy at low frequencies. Therefore, the water gun offers a very high resolution but limited penetration. Their utilization ended in the 80s. The water gun compressed air pushes the shuttle, which shoots water, producing cavitation. Such a vacuum implodes, generating a shock without creating a secondary bubble. Vapor shock and starjet are based on the principle that steam does not generate a bubble effect in the water. These sources inject steam, generating a precursor. As the bubble expands, its internal pressure decreases and starts its implosion, which ends in a shock of the water against itself. Vapor shock is just one gun fixed to the boat with a rigid insulator. Therefore, the crew felt each shot very well. In the starjet, the precursors are inhibited by using from 1 to 4 subarrays. Each subarray has 4 guns emitting different bubble periods and synchronized on the implosion peak. Starjet is a punctual source with excellent repetitivity but low penetration. Starjet industrial use began in 1982, but ended in the 90s, also because only fresh water had to be used for the source. For the airgun, dynamite was the common source for marine seismic operations. They were placed on the seabed or directly into the water, with dramatic production of noise. Maxi pulse is a dynamite source where bubble oscillations are recorded and used to compute the bubble filter, allowing to convert the data to zero phase. In aquapulse, an oxygen-propane mixture is exploded inside a closed flexible chamber, which reduces the bubble effect. The source signature is nominally minimum phase, but effort is required to correct the timing variation. And the negative side of this source are the low resolution and the peak-to-peak energy. Second shock, electric shock consists of two plates separated by a chamber, where the air is pumped in. The plates are unlocked and propelled against each other by the hydrostatic pressure, creating a shock wave in the water. It is an implosive source without bubble effect. The emitted pulse is very short, a few milliseconds, allowing high resolution, but with a very poor penetration. Sparkers generate an acoustic shock via an electrical pulse, which vaporizes the conductive medium of seawater followed by implosion. Different sparkers are used at a depth from 5 to 4,500 meters, with a vertical resolution between 4 centimeters and 3 meters. High resolution seabed for hazard investigation, for instance, well site survey and offshore wind farms, is a typical application. Airgun is the dominant seismic source since its introduction in the 60s. Compressed air pushes down the shuttle and the reservoir is charged. Then the shot follows, generating a bubble. Here we have the airgun before and after the shot. Before and after the shot. After the shot, the volume of the bubble expands, losing internal pressure until reaching equilibrium with the hydrostatic pressure. Then the volume decreases, the pressure and the temperature increase, and the second shot follows, and so on. Therefore, the primary shot is followed by sequence due to the bubble effect. Delay between the shot and the bubble effect is a function of the airgun. Greater the volume, the longer the delay. Here, in this diagram, you can see the volume of the guns and the time. An airgun array consists of different guns with appropriate volumes in order to put in phase the main shot and phasing the bubble effect. Normally, each source is composed of 2 or 3 subarrays, each array having different gun volumes to reduce the bubble effect. You can see here the correspondence between the figure and the hardware. Here you have the typical shooting of an airgun array. And you can see the shot, bubble shot, then bubble effect. Now, how, here again we have a explosion. The point is how we can reduce the bubble effect in order to improve the signature of airgun. In the GI gun, by Sercel, we have a very important primary to bubble ratio, about 20%, and this is caused by decreasing the bubble effect. A GI gun is made of 2 independent airguns within the same casing. The first airgun, the so-called generator, generates the primary pulse and creates the bubble. Just before the bubble reaches its maximum size, the second one injector injects air inside the bubble. The second injection prevents the oscillation, resulting in a clean acoustic signal. In the G gun, when the solenoid valve is energized, the triggering chamber is pressurized, allowing the shuttle to uncover the port, and high-pressure air is released into the water, generating the main acoustic pulse. When the pressure within the main chamber drops, the still full pressurized return chamber pushes the shuttle to its pre-fired position. Important to notice that the gun is an array that can be easily changed from 25 to 150 cubic inch by means of inexpensive plastic insert called volume reducer, and from 150 cubic inch up to 520 cubic inch by changing the external body, retain the same mechanism for the entire shooting sequence. This is the source. In the source, the air release is lowered compared to a conventional air gun, reducing the bubble effect, both slowing the speed of the shuttle and changing the shape of the output port. These features compare the standard air gun shot on the left versus a source on the right. Source reduce very high frequency output, and it is marine mammals friendly, but it is 25% more expensive than conventional lead-ion air guns. Here you have the Blue Pulse source by Sercel. It's an innovative evolution of the G-Source 2 marine source, designed to mitigate the high-frequency footprint of marine acquisitions. Available as a dedicated source or as a low-cost, straightforward upgrade of G-Source 2. Here you can see the comparison between the different power spectrum of the Blue Pulse source. We can see that the Blue Pulse source is a Sercel answer to the Teledyne A source. Same enhanced operation performance as a G-Source 2, but with an upgraded kit, allowing to mitigate the high frequency. Then we have the Schlumberger as a drop the Hypercaster, an airgun source for borehole seismic surveys. This array offers enhanced low-frequency spectral content using a two triple gun cluster. Is such that the two pressure fields produced on firing interact and oscillate at a frequency equivalent to a large single gun of equal volume. The result output from the array is a broader bandwidth signal that enhances ESP application, subsalt imaging, deep water and deep wells, and the calibration of complex surveys, anisotropy, AVO, etc. And now I thank you for your attention, and I leave the stage to Dr. Walker, who will start describing the E-Seismic, the continuous wave fields on the source and receiver side by PGS.
Thank you, Luca. Yes, I'm Chris Walker, Chief Geophysicist with BGP Offshore. If we can, as Luca says, this is the PGS E-Seismic source, continuous wave field. It's a time-distributed source where rather than firing the guns simultaneously, as we have in traditional airgun sources, essentially you've got a continuous firing of the individual guns. So you go away from the idea of an individual shot record, and in the E-Seismic method, the seismic sources, the small airgun sources, are essentially trying to emulate a white noise sound source, so that it's continually emitted whilst the vessel is moving, and continuous source records are then sliced from the continuous data. Individual source records are extracted from the continuously recorded data, and the technique uses very dense randomized time intervals. And so this is a data example from offshore Brazil, where we see in green the very small amplitude individual gun pulses compared to the conventional airgun source shown in red. And with the E-seismic using a hexasource configuration, we're able to get very good penetration, even though we're using very small gun volumes from the E-seismic data. And I think that's because the bubble pulse energy that's normally used in a tuned array to cancel out the bubbles from the bubbles radiating from the different gun volumes is actually penetrating into the subsurface. So if we have the next slide, please, Luca. So we, by having this continuously emitted source wave field, we can actually get better source side sampling. Obviously inline, because you can choose because you're emitting the signals continuously, you can choose your shot interval to be as small as you like. And then by going to individual firing, closely spaced crossline sampling, you can get much better aerial sampling of the source side. And so we see in the graphics time slices displayed here, conventional dual source imaging with the E-seismic hexasource, showing better resolution from the hexasource data because of this improved source wave field sampling. There are no speed limits implicit in the method, so there's no clean record requirement. So you get improved operational efficiency, and potentially you can go to as many sources as it's physically able to deliver air to from the seismic vessel itself. And obviously, as Luca talked about, with the new the Teledyne's E-source gun and the Blue Pulse, we have reduced the acoustic emissions by going to much smaller source volume, so we have less environmental impact, as you can see from both the sound pressure level, quite dramatically lower, and also the sound exposure level compared with a 4,130 cubic inch gun. We see much less environmental impact. Next slide, please. So moving on to developments on the low frequency side of the airgun sources, this is ION's Gemini source. And if we can just step through the slide, please, Luca. This is actually, it uses, thank you. It uses two 4,000 cubic inch chambers with a 2,000 PSI firing pressure, but its parts, like the E-source, have been modified to better control and the creation of the air bubbles and subsequent oscillations. So we end up having a very broad frequency spectrum that is lower because of the large volume in low frequencies, with a very high signal to noise ratio compared to conventional sources. If we can go to the next slide, please. We see the spectrum compared of the 8,000 cubic inch source in red, showing a peak just below 3 Hertz, compared to a 5,000 cubic inch conventional source. Both sources operated at 2,000 PSI. So we do have much richer low frequencies from the Gemini source as advertised. But what's also interesting is that we are seeing a lower high frequency output from the source array as well. So it actually is improving the low frequency output and reducing the high frequencies that we don't use for conventional seismic imaging, and so has less impact on the environment. Next slide, please. So this is Shuki Ronan's low impact seismic source, so now a Sercel product. It's called a tuned pulse source, and Shuki has gone to the other extreme. Obviously, as we go to large gun volumes, we get bigger bubbles and lower resonant frequencies. This is a massive 26,500 cubic inch gun, but it operates at 1000 psi. So when it's fired, it doesn't so much shoot as rumble. And again, the resonant frequency for this gun is just below 3 hertz. And we have, again, as with the Gemini source, we have lower mid-frequency output by approximately 12 dB. And the high frequencies, again, because we're operating with very large volume and lower firing pressure, we have a very significant reduction in the high frequency output. Next slide, please. So again, the spectrum of the TPS, the tuned pulse source, is shown in red. And we have, sorry, in blue in this case, sorry, where we see the resonant frequency, as I say, just below 3 hertz, 2.8 hertz. And the same 5,000 cubic inch, 5,100 cubic inch array shown in red this time. Again, as well as the improved low frequency output, we see that the TPS does indeed have significantly lower, higher frequencies than the conventional airgun array. Next slide, please. So this is just a video. If you click on it, Luca, please. And it's a pretty big bubble, as you would expect from a 26,500 cubic inch array. So, sorry, not array, a single source. So next slide, please. So harmony is a technique that was first investigated in the early 1990s by Robert Laws, Les Hatton, and Paul Houtzen. So when air guns are operated close together, we get a frequency locking effect that allows you to get improved low frequency output from the cluster of air guns, even when the bubbles don't actually coalesce. And so you get the interaction through the pressure field known as frequency locking. And so this has been developed into harmony. It's a Shearwater source. So it actually gives you an alternative way of using conventional air guns with a different geometry to improve low frequency output. Here again, compared to a conventional array, we see about a 10 dB improvement in low frequency output at 4 hertz. So not quite as low as Gemini or TPS, but certainly better than conventional air guns. Next slide, please. So the application here primarily for improved velocity model building using low frequency data. So I'm now going to move on to marine vibrators. And why do we want to use marine vibrators? Well, initially it was to improve reduce environmental impact, but there are some geophysical benefits to having control of the phase of the signature that you're putting into the ground. And so we can get improvements in data quality, and also by using some novel techniques, get improvements in source productivity. So when we look here at the spectra, just go back please, Luca. If we look at the spectra that we see from a conventional airgun array, the potential injury zone shown in the plot at the top from a conventional airgun array, and BAS, which is the Shearwater's marine vibrator, showing that it has, because of the reduced sound pressure level, because it is a swept frequency source rather than an impulsive source, we're able to have much, much lower environmental impact. And I say that was the historical reason why people started looking at marine vibrators. And people have been looking at marine vibrators for a very long time indeed. And so the initial work was done in the 60s. Next slide, please. And they literally put conventional land vibrators onto heavy base plates on board the vessels, but they shook themselves apart because it just wasn't physically robust enough. And in the 1980s, there were marine vibrators that were used. When I was at GECO in the mid-1980s, we actually shot a production survey using IVI vibrators for Britoil in the North Sea in the UKCS. So they had an internal drive mechanism with a phase lock loop on it, and they tried to actually have a volume injection into the water to either have it using a hydraulic piston or a motor that changes the air pressure within the vibrator, or using electromagnetic type systems as you would do in acoustics with a loudspeaker. Next slide, please. So the main, say, focus has been to try and minimize the impact on marine mammals and marine life by reducing high frequency output. And when we look at a conventional air gun, I say 99% of the energy is contained within the first 30 milliseconds of the energy being released into the ground. With a swept frequency source like a marine vibrator, we're able to reduce the instantaneous sound pressure level by having the energy introduced into the subsurface over time. Next slide, please. So the rise time on marine vibrators is usually several seconds. The energy is transmitted over, say, a long period of time, 10, 15, with no data even up to 30 seconds. And although the maximum amplitude is much less, after correlation, you get very good data. Next slide, please. So the modular vibrator that's been developed, this is a flex tensional source that was initially developed by PGS, and it uses the displacement of many small surfaces to actually move the water that's required to generate the acoustic pulse into the water column and then into the subsurface. And so you can use different size units of these, different numbers of these units to actually have both a high frequency source and a low frequency source, like corresponding to a woofer and a tweeter in an audio type environment. And the flex tensional concept uses an electric driver and powerful magnets to bend the spring elements within the fiberglass shell that houses the vibrator. And so you actually can tune these to produce a resonant frequency. Subtone, one of the PGS units, has a resonant frequency just below 10 hertz. And then the other unit has a higher resonant frequency, just under 20 hertz. And by using them in parallel at different depths, you can get relatively uniform amplitude output over a 5 to 100 hertz band, and they are operating, say, at different depths. Next slide, please. So you've got the sound pressure level and the sound exposure level are used to dictate how surveys may operate. And so in this next slide that's coming up, we see the sound pressure level of a 3090 cubic inch gun compared to a 150 cubic inch airgun array, which is actually very comparable to the marine vibrator output. So we're able to get essentially the equivalent of a 150 cubic inch airgun array into the ground when we're using the marine vibrator. Compare, obviously, you've got significantly less. You're looking at more than 20 dB lower peak amplitude from the marine vibrator array compared to the 3090 cubic inch conventional array. So why did it not work in the late 1960s? I think really you had two major factors. One was the practical issues of having a moving source with a long randomized signal. You needed to have long record lengths, shot record lengths, in order to get the energy into the ground. There were obviously a lot more processing required. I think what we've seen also was that the reliability of the units was questionable. So there was two aspects. There was a practical logistical aspect and the operational efficiency. So why are they actually being revisited today? And I'm going to go through what's happening today. So you've got environmental concerns, particularly in areas like California and Brazil, either seasonally or permanently. And so there's a lot of emphasis trying to remove marine pollution, acoustic pollution. And also people have been looking at trying to get better low frequencies, as we've seen the developments on the airgun side, to try and get better FWI-based velocity analysis. Next slide, please. So the marine vibrator is currently being developed, in operation. There's the Joint Industry Project Vibrator, which I'll describe in a minute. There's AquaVib, which is the extension of the PGS vibrators that I described earlier, that's been operated now by SA Exploration. There is bass, shown here in the bottom left display, and that's the Shearwater source. And there's Wolfspar, BP's 30-ton, very low frequency Hummer rather than a vibrator. Next slide, please. So the JIP vibrator, a joint industry project, which has been sponsored by Shell, Total, and Exxon. Each vibrator is designed to replace an airgun. It's about the size of a small car, and each unit is integrated projector node, as they call it. It weighs, it's not light, it weighs 2,500 kilograms and is 1.5 by 3 meters by 1.3 meters. So it's a pretty substantial beast. It has a power amplifier, a transducer, and a control unit. And the intent here, next slide please, is to have 6 of these towed below a subarray. So I say each IPN replaces a conventional airgun, and we have 6 IPNs per subarray, and so you end up with something like 36 of these on a conventional dual source or 6-string operation. Next slide, please. Again, we see the spectral comparison on the right-hand side, the pressure output on the left here, comparing the marine vibrator in green with a 3,000 cubic inch airgun in red, 1870 cubic inch airgun in blue. Obviously, the instantaneous sound pressure level is much, much lower. And we look at the frequency spectrum, we see we're only putting energy from 0 or 5 hertz to 100 hertz into the ground, compared to the much broader spectrum of energy that we're emitting from the airguns that we don't use for imaging. Next slide, please. I say the Aquavib from SA Exploration is designed for shallow water operation in a catamaran type vessel, where the units are hoisted up for transit and then lowered into the water for operation. And, you know, as with the PGS system, the separate units operate at different frequency bands, and the system has been used. Next slide, please. In production, this is data taken from the Gulf of Mexico, but it's also been used in environmentally sensitive areas in Southeast Asia more recently. So on the left, you have a section generated using a 900 cubic inch airgun source, compared with the Aquavib Symphony, which is SAE's broadband operating the lower frequency source at a deeper depth than the higher frequency source, giving you very improved resolution compared with the 900 cubic inch airgun array from the Aquavib system. Next slide, please. This is Shearwater's broadband acoustic seismic source, very clever acronym, BAS. It's got separate units for different bandwidths. The units themselves, again, are fairly large, 2 meters by 2 meters by 3 meters, and weigh 5,000 kilos. The intent here is to deliver improved geophysical data quality and higher operational performance from the units, because you've got control of the frequency and phase output of the units. And because you're able to go to very complex coding sequences, because you have complete control over the phase and amplitude of the devices compared with an airgun, you're actually able to get much higher multiplicity sim source from these devices. And then somewhat uniquely, by going to what I would call a vector source, a gradient source, by operating the units out of phase, you're able to replicate on the source side what the isometric system does on the receiver side, and you can actually interpolate shot positions or sweep positions. Tim will be able to answer questions on that afterwards, I'm sure. Next slide, please. So these are some pictures that Tim very kindly provided for field tests for the BAS system, showing the units being lowered into what looks like a Norwegian fjord. Next slide, please. So with the BAS system, we can actually put in phase encoding, and we can use source gradients. And the different size, different frequency units operate at different depths. The lower frequency units, which are required to sweep less often because they're longer wavelength, are towed at a deeper depth, and then the mid frequencies at shallower, and the higher frequencies at the shallowest depth of all. And so you can have frequency dependent shot intervals. As I say, the lower frequency sources don't need to be swept so often. You can have different sweep designs. As I say, you've got complete control over both the phase and amplitude of the signals that you're injecting into the ground. Next slide, please. So with the gradient source, the objective here is to actually operate the vibrators out of phase so that you generate a gradient signal. So you're essentially sending out a vector signal from the sources rather than a scalar signal from the sources. And this then allows you to interpolate source locations. So with a conventional omnidirectional source, the vibrators will be operated in phase. With the gradient source, they're operated out of phase. Next slide, please. And what this does is give you a vector quantity that you're putting into the subsurface, and as such, by measuring the gradient of the source field, you're able to interpolate source positions. Next slide, please. So with this technology, Shearwater claim that they can improve the operational performance by a factor of 3. So with a conventional source array for this particular source geometry or receiver shot and receiver geometry, we're using airguns where you'd have 13 source lines and would take 36 hours to shoot. With the marine vibrator using a gradient source, it would only actually take 12 hours to shoot the same, the sweep lines, which are then interpolated to give you the equivalent of the 13 source lines that you would require with an airgun source. So a very significant improvement in operational efficiency. Next slide, please. So Wolfspar is BP's 30-ton low frequency, ultra low frequency. Its resonant frequency is actually down at 1.8 hertz. It can sweep up to 8 hertz. When it's been used in operation, they've used it to hum at about 1.8 or 2 hertz. It is a monster. It's 1.6 by 1.6 meters by 10 meters long. It has to be that big to displace the amount of water that's needed to generate signals at 1.8 hertz. It's towed deep, 30 to 60 meters, and it's not designed for imaging. It's designed purely for FWI-based velocity model building. Designed for deep water. The intent is to get better low frequency data, especially below the salt in the Gulf of Mexico. Again, you have higher operational performance because it's a controlled frequency source, and you can get higher multiplicity sim source through phase encoding. Next slide, please. So this is the Wolfspar source in red. You see its resonant frequency there at about 1.75, 1.8 hertz compared to the airgun array. And they've used this in a number of surveys in the Gulf of Mexico, in addition to their conventional airgun sources, to provide velocity information. And the slide on the right, on the graphic on the right, shows data streamed back live from a test use of the system over at the Atlantis field in the Gulf of Mexico a couple of years ago. Next slide, please. So moving away from marine vibrators, the final few slides here, GeoSource is a technique developed by PGS that is distributed in both time and depth to give you the ability to remove the receiver ghost on the source side. Going to multi-component streamers allowed us to remove the receiver ghost on the receiver side. GeoSource allows you to do the same thing on the source side. So the depths of the subsources are chosen, so the ghost functions are complementary to avoid any deep notches in the spectrum, and by having the firing time delays so that each source is fired so that the subsurface illumination are identical, and the receivers, you offset the sources and receivers to give you the same subsurface coverage. So we end up getting a receiver, this ghost notch on the source side can be removed by using these time and depth distributed source. Next slide, please. So you use a weighted summation of the emitted wave fields, and you end up, by going through the maths of this, removing both the source ghost function and the receiver ghost function, so you end up having a whiter spectrum as possible. Next slide, please. On the near-field hydrophone side, there's been work done both by Shell and DUG recently, where people are putting out 2 near-field hydrophones per gun or cluster to allow you to make better estimates of the sea surface ghost. The Tsiolkovsky notional source method assumes a reflectivity coefficient for the sea surface ghost, and in practice, especially in variable weather conditions, every single processing contractor has had to modify the sea surface reflection coefficient over time to actually get better match between the far field signature predicted from the near field hydrophones and the data recorded in the streamers or in the nodes. So by using the 2 near field hydrophones, the notional ghost can be calculated as well as the notional source, because you've got twice as many unknowns, you need twice as many measurements, and so we end up having a better near field hydrophone prediction or far field signature prediction by using both the single and dual phones, by using dual phones. Next slide, please. I'm running out of time here. Flexible source steering. This is from Sercel. It's a winch-based steering system to allow you to actually control the source positions and the width of the source in different weather conditions, and to give you better source positioning control, especially for 4D. Next slide, please. And so this is the Sercel, is the steering assistance. It's integrated into the navigation system. It allows you to take care of automatically variations in the sea current and any other environmental phenomena, wind, wave action that can move the source position, improves 4D source positioning reliability. And so next slide, please. So there's a system developed here, which is allows you to develop by Evotech, which provides the same kind of capabilities, but you have a source steering control system to improve 4D positioning stability. Next slide, please. So that's all the material I plan to present. This is a pitch, if you like, from the community. This community we have is designed to bring together as many people as possible across the industry, professionals, researchers, academia, students, to try and share knowledge and develop skills. So it's something we encourage everybody to participate in, and we hope you found this particular presentation useful. Thank you. So I'm not sure whether we have any questions in the chat.
No, there are no questions in the chat. Maybe anyone has a question, you can also unmute yourself and introduce yourself and ask your question.
Yeah, maybe I can. It's Frans den Grode here. Can you hear me all right?
Yes, indeed.
Excellent. I have a question to Chris Walker. You had a slide on eSeismic. Yes, and that slide said that the sound exposure level is below that of an airgun array.
Yep.
That is not immediately intuitive to me. Maybe you can explain.
It's this slide. If we go back to this slide, this is I think it's because the actual, although it's the same number of air guns being used, because they are being fired over a much longer time interval than the actual conventional air gun array, then you end up getting a reduction in the sound exposure level as well as the sound pressure level. So I think it's to do with the fact that you're firing continuously, but you're not trying to fire all 36 guns, if there's 36 guns in the array, every 10 seconds. So you're actually firing the guns over a longer space of time. That's the only, I got these slides from PGS. I didn't dig into it, but that's my understanding of it, is that you're actually, you're distributing the energy over a longer exposure time. If you were firing all 36 guns every 10 seconds, the SEL would be the same.
Yeah. But in terms of environmental impact, I mean, for a survey of 3 months or so, the same amount of energy would be emitted, I believe.
Not if the effective time distribution of the small gun or individual gun firing is longer than it would be if you were firing a source every 10 seconds or 12 seconds or whatever it would be.
Okay, I'll take that over. Thank you.
No worries. Any other questions?
Yeah, maybe one more around this dipole marine vibrator,
Right.
created by Shearwater to enhance productivity. On land, we have traditionally enhanced productivity by a technique called slip sweep. Is that something that could compete with this?
Tim, are you online?
Yeah, I mean, I can answer that. I mean, I think there's a number of different aspects, ways in which we can use marine vibrators. On one of the slides I showed, we use phase encoding to have multiple units. So the plan is to use multiple simultaneous units sweeping. Now, of course, you can do that with air guns. We use different techniques to simultaneously shoot with air guns, but when you use phase, you've got you can have a larger number of units, and your separation techniques are improved. I think you asked about dipole sources. So again, there, what you're doing is if you think about the wave field, instead of having a scale, you've got an additional measurement basically if you're measuring the gradient there. So you've got that with that additional measurement. If you think about receivers, it improves the interpolation. It enables you to interpolate. It's not giving you another measurement there, and the same is also true with sources, with dipole sources. So it doesn't completely remove the need. It's not a sort of magic bullet, but it does enable you to interpolate sources much more effectively. So
I understand that, Tim, but my question was really onshore. You use slip sweep techniques for independent vibrators to operate, to sweep a little differently and can separate the signal afterwards. That's a well-known technique onshore. Could that be used offshore as well? Could that compete with your dipole followed by interpolation technique?
Well, yes. I mean that is. I think I'm running. I understand what you're saying. You're saying you have simultaneous units sweeping simultaneously, right? In different.
Absolutely, but then a little different in time. Yeah. So the upsweep is shifted in time. That's the way you separated them in the frequency time domain.
Sorry to interrupt, Tim. You could use slip sweep, but we probably aren't going to have as many vibrators operating in the marine environment unless we go to a radically, Delphi type system.
Yeah, so I'm not sure how many vibrators Shearwater is planning to use. You mentioned 36 or so for the chip.
I think you can use slip sweep, but I suspect there are going to be better coding sequences because you have more consistent coupling in the water than you do on shore.
That's
so
true.
I think the idea of doing phase encoding and some of the sort of radar and acoustic type coding sequences that are used to allow you to get simultaneous source will actually give you better separation than simply slip sweep.
Okay.
Remains to be proven, but because you've got just about perfect coupling in the water column compared to land, I think you're going to be able to do things with marine vibrators that we would struggle to do because of the inconsistency of base plate coupling that we see onshore.
Yeah. And how many vibrators would a BAS system consist of?
You mean a single array, if you like, or
behind the boat. So how many would you go behind the boat?
So probably between initially we plan to probably use 3. So an array would consist of different units at different depths. But I should imagine possibly we probably go to a larger number than that, possibly 5 or 6.
Thanks.
Hi, I have a question here. This is Damien Dionangar. It was a question regarding if any one of you could comment on the reliability of this marine vibrators. It was mentioned early on that it was unreliable because of the tough environment, but that seems to be a comment from the past. And I was intuitively we have big air guns like making a massive amount of air gun oscillation and lots of movement in the water, and you could move to marine vibrator with a much smaller amplitude of movement. So from a mechanical standpoint, you could potentially think that it would be more reliable. So I just wanted, if anyone could comment on how much the reliability was into the development of maybe the different solution, and shouldn't this be a selling point to the technologies in addition to the environmental benefit? When we see like air guns are reliable, but they do require a lot of maintenance, a lot of people on board, and some relatively risky operation when you have to bring the air guns on board, etc.
It's a very good question. I'll let Tim answer for Shearwater, but remember, if you look at airgun performance now compared with what it was like when they were first introduced, there's a world of difference. Back in the 60s, if an airgun survived a complete line of 20 kilometers, it was rare.
I mean, I agree with what Chris has just said. I mean, air guns are very robust these days, and the downtime on a typical survey for air guns is almost non-existent now. I can't, it's one of a few percent. It used to be many more percent than that. So air guns have improved in reliability. I think with marine vibrators, I mean, there'll be a learning curve, like with any new systems that are introduced. There's bound to be a learning curve where we start off with maybe higher technical downtime, and then we improve that. So, yeah, these systems, the quality of the systems that we can build nowadays is much. We can model these things. For example, we can create whole sort of systems, digital twins as we call them, prototype systems in a computer, and model them under operation, and try and figure out what are going to be the weak points. We couldn't do that 30, 40, 50 years ago. So I anticipate when we introduce these marine vibrators, there'll be a bit of a learning curve, but I hope we'll get very good reliability figures out of them.
Yeah, and I think that's very true, Tim. I think the other thing to bear in mind is that a lot of the airgun technical downtime on a towed streamer vessel can get hidden because you have fairly long line changes when you're doing large spreads, 12, 16 streamer spreads, 8, 10 kilometer streamers. Line changes can be, guns can be pulled in and replaced and repaired, etc. But you're right, the intrinsic reliability of the airgun is an order of magnitude or more better than it was, even 20 years ago, because people have improved the maintenance and it's really just refine the technology. And as you say, I suspect marine vibrators will follow the same route, but much faster.
And if I can just add, the BAS system anyway, or the base system as it's sometimes called, is designed for 100% duty cycle, so it's continuously vibrating. There is no listen time, if you like, or a point at which it's not shaking. So these things vibrate continuously. So it's got to be able to do that, and no line changes. That's the spec. So
that's impressive.
It'll shake continuously.
That's impressive.
Yeah, I mean, it's a lot of interesting comments. It's just my own. Some of my own view, and I was looking at this, and I was like, the things around the maintenance and what's the planned maintenance of those systems. How does it, impact where you will deploy which kind of vessel, and we are moving towards, less and less people on vessel, potentially fully automated vessel. are those systems actually a better answer than airgun for the future? And should it be, you know, an actual
I mean, one of the things
of development and selling point and where you should put in addition, I mean, the environmental stuff is great, but you know, if you can at the same time show that's where we will get, you know, lower cost, more efficient surveys, and actually better for then you have a complete package.
I think that, Damien, I think that's a very good point, because one of the things that people tend to forget about is the fact that you've got, you know, the airgun reliability, as Tim says, is fantastic, but you're driving it from compressors, and those compressors require significant maintenance and staff on board the vessel. The actual, if you look at the overall system with a marine vibrator, with the power drive and all the rest of it, it's actually simpler, and you could conceive of an unmanned marine vibrator source vessel much more easily than you can conceive of an unmanned airgun vessel, because you don't have compressors on board. Now, I know there's been small volume sources tested on a lake by Shell, automatic, you know, with looking to try and get an unmanned source vessel, but so far they've been very small source volumes used for relatively limited periods of time. But I think it's conceivably be much easier to look at an unmanned marine vibrator vessel in the future than an unmanned airgun vessel.
Another comment, if you don't mind, it's also a fact that the marine vibrator is by far, right or wrong, we can discuss for hours, but it's considered by far more environment, let's say, more environment suitable in a certain area, as was said before. So I think the future, take it or leave it, is the marine vibrator.
Absolutely, Luca. Absolutely. You know, it's been one of the principal drivers. But I think the message that Tim wanted to get across in his slides, and I would reinforce it, is the fact that you have potentially both geophysical data quality and operational improvements that will come from marine vibrators that you won't get with airguns. So in addition to having a more environmentally friendly source, you can actually get better data quality and improved operational efficiency. So it's like a win-win-win.
Yeah, one of the big benefits, I think, with a marine vibrator is with an airgun, typically we have a sort of surplus of energy in the mid frequencies. So we have, you know, in the sort of 10 to sort of 50 hertz band, we have this surplus of energy, but it drops off at the low frequency end and the high frequency. Now with a marine vibrator, you can have much more precise control over that output. So you can design your sweeps and your sweep lengths to give you kind of a constant signal to noise across the full bandwidth. So potentially improving the signal to noise at the low frequency and the high frequency end. So the control that you have with a marine vibrator potentially gives you a lot better data. So that's something that we aim to demonstrate when we first deploy these units.
Any other questions?
Not for me. Thank you very much, gentlemen.
No, thanks for your questions.
Okay, thank you everyone for watching. The recording will be made available on our YouTube channel, EAGE Communities. And I wish you a very nice day.
Thanks a lot, Karen.
Nice day. Bye-bye.
Thank you.
Thanks.
Thank you, ladies and gentlemen.